Hi, my name is Brian Caffo, and this is a lecture on generalized linear models, binary data. This is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay. Frequently, we care about outcomes that have two values. For example, if we're doing survival analysis, we're interested in alive versus dead, win versus loss, success versus failure, and etc. And these are called binary Bernoulli or 0-1 outcomes. The most common, let me expand on this. The most common version of binary outcome that I personally deal with is diseased or not. I tend to work a lot in developmental disorders, so the outcome that I might look into is something like a developmental disorder like autism or attention deficit hyperactive disorder. So that might be the outcome, and I might be interested in sort of how brain measurements predict those things. And then there's Bernoulli outcomes, which is just a 0 and 1. But if let's say if we flip a coin a couple of times, those are all exchangeable because they know none of the covariate values have changed. So instead of analyzing the individual 0 and 1s, we might analyze the count of 0s and 1s out of the number of flips, and that would just be called binomial outcomes. So the same model for Bernoulli outcomes kind of apply for binomial outcomes. So here's the Ravens data. Baltimore Ravens is an NFL football team located in Baltimore, which is the city that I live in and like very much. So you can get the data here, and you have to load it up by loading the data. And head just prints out the first couple of rows. Okay, so here's the variables, and imagine trying to fit a linear regression model to this. It wouldn't work very well, right? So here's a 0 or 1. If the Ravens won, we'd have an intercept, a slope, the number of points. So we're trying to use the number of points to predict whether or not they win, and additive error. So this, obviously doesn't make a lot of sense because, this additive error is going to make it so that this guy isn't 0 and 1 if the error is, say, continuous. Otherwise, the error would have to depend a lot on these values in order to make this always be 0 and 1. So here you can fit the linear regression. I don't think it's the particularly great thing to do. I would also say, by the way, it's not a horrible thing to do either. If you're interested in predicting a Ravens win versus a loss, and you just create a threshold linear regression estimate, this isn't the worst thing in the world to do. It's just not very interpretable, and right. And in this class, we're interested in interpretation. So if from a machine learning perspective, depending on the loss function, a linear regression might be perfectly reasonable for binary outcomes. But for interpretability, you want something different. So let's talk about things like odds, and this is a way to fit to reframe the model in a particularly interpretable way. So the binary outcome is 0, 1, whether or not they won. We could talk about the probability that they won given the parameters in their score, how many points they scored. The odds, remember, is the probability over 1 minus the probability. And the log odds is, of course, just the log of the odds, but the log odds is also termed the logit. I think a term that was invented by a person named Berkson, who was an alumni of my department a while ago. The department here is actually quite old. It's a 100-year-old department. I think it was the first department of biostatistics. So linear regression would do this, right? Directly fit the wins with an additive model, or you could just say the expected value. If we expect to value both sides of this guy, you get this equation because the expected value of the error would be 0. Logistic regression instead models this. The probability has to look like that, or this same equation rewritten is that we've modeled the log odds of the probability of winning given the score and the coefficients as being this linear predictor. And that's what we did exactly on the previous slide. So this probability, this probability right here we defined as mu I, and so this is log of mu I is equal to, and this is eta I right there from the previous lecture. Okay? There we have, now we have the equation rewritten. How do we interpret these guys? Beta 0 is the log odds of the Ravens win if they scored 0 points, right? Because if I just plugged in 0 there, that guy would go away and we just have beta 0. Okay? Beta 1 is the log odds ratio of win probability for each point scored. So let's just look at this, right? So we have what would be the so the log odds odds if they scored x plus 1 minus the log odds if they scored x would work out to be beta 1. Okay? And because this this is a subtraction of two right? It's the log of the odds, right? And because it's the subtraction of two logs, right? That's equal to the log of the odds if they scored. It's the scored is scored equals x plus 1. Point scored equals x plus 1 versus the odds if scored equals x. Okay. So that's why we consider it the log odds ratio. And then, by the way, is equal to beta 1. By the way, we can get rid of the log if we take e to this side. If e to both sides, we'd get rid of the log, and we get e to the beta 1. So e to the beta 1 is the odds ratio, whereas beta 1 is the log odds ratio. Okay? So if you want to interpret things back to the odds ratio. By the way, we don't have any other covariates here, but if we had other covariates, we'd have to add the phrase with all of their covariates held fixed.